As far as the preparation of the alkene, so we'll take a look at now competing reactions. So we can look at a substitution reaction, and as we did last week, you should be able to identify all the bonds that were broken and formed. So when we go through and look at that for our substitution, what bonds were broken? Carbon and iodine, good call. How about for the bonds that were formed? Carbon and the chlorine, okay? So finding those patterns and identifying what things changed can then allow us to apply and start to come up with reasons why things happened. Okay, so we could look at this reaction and say iodide was substituted for the chloride. Okay, so we're just trying to come up with patterns. When we look at the next reaction, okay, in this case it's an elimination, what bonds were broken? See the carbon iodide, anything else? How about bonds formed? We got a carbon to carbon double bond. Is that everything? As a hint, I'll even color code it. What the heck is that? That H plus had to come from somewhere. We lost a carbon-hydrogen bond as well. Okay, if you thought substitution was difficult, at least all the pieces were immediately visible. When we move into elimination reactions, we start to imply our hydrogens. We often forget them and stop realizing where they're coming from. Okay? So be aware that those hydrogens are going to play a really big role as far as our elimination reactions go. Okay? In this case, what we did is we eliminated a small molecule. In this case, our molecule was HI. Okay? It was eliminated from the structure. Okay? So now the trickier part is then going to come up with, well, what's the difference between these two reactions? Okay, so now it's again going back and comparing these. We're starting with an alkyl iodide. The iodine leaves. We end up with some kind of alkyl compound at the end. Okay, so a lot of the characteristics or the mechanistic steps are going to end up being the same. So what's the biggest difference between these? What's a difference between them? That's a pretty big difference. I got a double bond. What else was a big difference? Okay, why is the double bond not going to be an important thing to look at? On a test, you might be asked to say, predict the products, which means you don't have the products in front of you. You have to be able to look at the reagents and decide, based on those chemicals, what possibly occurred. So what else is the difference? The what? What proton? So good call, finding another difference, but again, that's in the product. We need to be able to look at the reactants to be able to decide or look for that difference. Chlorine. Yeah, there's a chlorine. What did that chlorine do in this reaction? What did it act as? It acted as a nucleophile. So one of the things that we are required to have for a substitution reaction is a nucleophile. If we lose the nucleophile, we can't do a nucleophilic attack. We can't do the substitution, in which case we have to come up with some other way to stabilize our intermediates, and that's where we get the elimination occurring. Okay? So you need to be able to look for these patterns, look for these differences to try and determine what happens in each case. Okay? That on its own wouldn't be complex enough or difficult enough, so we're going to take it a step level or make it a little bit more difficult and change our functional group to an alcohol. In theory and lecture, you've already seen your alkanes, and you should be aware of the reactivity of our alkanes, ultimately nothing. Okay? London dispersion forces, relatively low melting points and boiling points, so not particularly interesting. We move that up to the alkyl halides. When we get up to the alkyl halides, we increase the intermolecular forces, which means we increase our melting points and boiling points. And we also introduce the reaction or a reactive site. We get that electrophilic carbon. Okay, that allowed us to do our substitution reaction. Okay? When we move up to the alcohol now, we get an even stronger intermolecular force, even higher melting points and boiling points, and this is where our alcohols become the most frustrating or irritating, is how many different things can possibly react. Okay? We get an electrophilic carbon. We've got a nucleophilic oxygen. We have a Bronsted-Lowry basic oxygen. We have a Bronsted-Lowry acidic hydrogen. All of these things are possible types of reactions coming from the same individual compound. So depending on what other chemicals are there, what other reagents are there, you're going to end up seeing different results. You have to be able to evaluate the reactivity of each of those sites and try and process and predict what happens. Okay? So the alcohol as a functional group is synthetically extremely useful because of all of those different reactions, but as a student, it's probably your least favorite because of all the different things it could possibly do. And you now have to know all of those possible things. Okay? So, if we move up to reactivity, and we wanted to do a substitution, okay, because that one's a little bit more straightforward, got a little bit of practice with it, that one might make a little more sense. So in the case of the alkyl halide, our nucleophile attacks our electrophilic carbon, kicking out our leaving group, in this case X. Okay? And that worked fairly well with our halides. When we move to an alcohol, we still have an electronegative element that can still take electron density away from our carbon. Okay? Except that when we try and run that substitution reaction, we don't get a reaction. Okay? The alcohol, for it to leave, it would have to leave as hydroxide. And that is a terrible, terrible leaving group. Okay? So we have to have that good leaving group. So what we're going to have to do is activate our alcohol so that it can actually react. Okay? What makes the alcohol a terrible leaving group? Our leaving group needs to be stable. What makes our alcohol unstable? Our OH unstable. It's not positive, but negative. We have a negative charge. If we have charge at all, that's typically a bad sign. Okay? Because that's something that's higher in energy. Okay? How can I stabilize that negative hydroxide? I need to add something positive to it, like a hydrogen ion. Okay? I add H plus to that, and what do I get? Water. How stable is water? Very stable. Okay? So I need to somehow convert my alcohol into a good leaving group. What I'll do is require this activation step and react my alcohol with an acid, turning that OH group into a good leaving group. So we're going to have to always start off with an acid-base activation to facilitate the reaction. Okay? This is a summary of resonance and mechanistic steps, different things to kind of go through. It'll also be the very last slide to help out with the assignment. Okay? This is the explanation of why. For everything that you do in both the lecture and in the lab, it almost always comes down to dealing with resonance and mechanisms, being able to move electrons. Okay? So you should be very familiar with these rules and be able to apply them correctly in every single case. When we go to the elimination in lab, for the interest of time, I'm going to pull the magic of the next button. Instead of drawing it all out, ta-da, there it all is. Okay? Our very first step must be that acid-base activation step. Our alcohol will act as a base, donating its electrons to our hydrogen ion. You'll notice our arrow starts where we have electrons, the lone pair, and it ends someplace that's lacking them. Okay? So all we've now shown is the sharing of electrons. That takes us to our next product. Okay? So when we're drawing a mechanistic step, I only care, particularly for this first one, just about that. Okay? My final product is irrelevant. Okay? Because my mechanism is only concerned about a single step. Okay? Once I've got that established, I can now try and evaluate the stability of that intermediate. That positive charge on an oxygen is a bad thing. Oxygen needs to pick up some electrons. Where's the easiest place it can get electrons? From the bonds near it. So it'll take electrons away from carbon. Would we expect oxygen to take electrons away from a carbon atom? Is that a reasonable thing to do? Yes. Why? Oxygen is more electronegative than carbon. It makes sense for it to take those electrons. We then draw the results of that. We end up with a positively charged carbon, not particularly stable, so I need to give it electrons. If this was a substitution reaction, I would then have a nucleophile floating around. The nucleophile could share its electrons, and we do the substitution. I don't have a nucleophile, which means I must find electrons from within the structure to stabilize. That's where we go and find that hydrogen. So we'll take the electrons out of that bond, put them into a double bond, and I now have my product. Okay? As a sidebar, let's just test to see what happens here, particularly with that intermediate. We've got a carbocation. Which of these carbocations is more stable? Left or right? The ones in red, that is. What makes the carbocations unstable? The charge. What charge is it? Positive charge. How can I stabilize a positive charge? I need electrons. Okay? So we evaluate the difference between these two structures. We've got hydrogens versus carbons on the outside of those cations. Which of those have more electrons? Carbon, which means which cation becomes more stable? The one with the more carbons around it. Okay? So it's looking for those patterns, looking for those ways to stabilize your intermediates that can allow a reaction to progress forward or to stall out and not occur. Yes?
Are hydrogens implied on the left structure?
To the exterior carbons, yes.
Yeah. Okay.
Why did I not draw them?
Because you didn't feel like it.
They weren't relevant to the question. That's the only real reason, yeah. Okay?
So the one on the left is more stable?
Is a more stable carbocation. And since we got enough questions about that, so a little bit of interest, we'll push it a little bit further. It's now a carbanion. Which of these is more stable now? Left or right? What makes them unstable? The negative charge. How can we stabilize a negative charge? Get it positives, but we don't really have any positives that we can bring in. Remember, this is organic chemistry. We're only concerned about the motion of electrons. So instead of bringing in positive, what do I need to not put near it? Electrons. So let's evaluate the two structures. Which of these has more electrons around it? The one with all the carbons, the one on the left. What did we say that we wanted? Less electrons around our negative charge, which means which one's more stable? Now the one on the right. Okay? So just by evaluating the things that make things unstable, ultimately our charges, and looking at electron density around each of these positions, we can start to come up with predictions about individual reactions. It's extremely helpful to try and simplify these as best you can. Okay? One more thing that we need to evaluate when we're looking at double bonds is the stability of double bonds. What makes all of these double bonds, all of these structures unstable? What's the most reactive part of each of these structures? Yeah, I heard it. Go ahead and say it again. The double bond. So we can look at that double bond. The reason that's reactive is we're looking at pi electrons. They're on the outside. For those to react, the electrons must come out of the structure. Okay? So if we look at those electrons coming out, what's circled over here? A methyl group. What does that carbon and hydrogen have around it? For it to be a methyl, what does it need to have? Carbon. And 3 hydrogens. What makes it a carbon? What makes anything an atom? Our electrons. So we're looking at a group of electrons. What happens as that pi bond with its electrons tries to go out that direction, what does it encounter? Encounters electrons. What happens? They repel and it comes back and sits back down. What happens when we go to the extreme case over here? Go that same direction. How many electrons does it encounter this time? As many? More? Less? Less. Which of those two double bonds is going to be more reactive? The one on the right, the one without electrons blocking our pi bond from coming out. Okay? We can use this to kind of determine or approximate double bond stability, and we can say that the more groups or non-hydrogen groups around our double bond makes our structure more stable. Okay? So the more substituted our double bond, the more stable it is. How is this relevant for elimination reactions? Well, according to Zaitsev's rule, the major product in an elimination reaction is going to be the one to be the most substituted double bond. You'll notice that I went through and have circled the substituents that we're referring to. So when we say substituted, they're all circled here. I'm not talking about the atoms within the double bond. Okay, I'm not talking about the internal carbons. I'm referring to the groups that are outside of that. So we get tetra substituted because tetra stands for, not fish, 4. Anybody have fish? You know what tetra? Okay, well, never mind. Look it up. They're pretty. There is an exception to the Zaitsev's rule. I don't know if you'll see it in lecture, but that's the exception. If you want to read about it, you can read about it. We won't see it in the lab. This is a summary slide of pretty much everything you're going to do as far as the procedure goes. Okay? Ideally, every step that you're going to go through. Okay? So let's push to the actual experiment. Are there any physical properties that we could take advantage of within this? Well, of course there are. That's why I asked. Okay? So what types of bonds are there in our starting material? Single. That's good. I don't like single. Go with something else. Are there any ionic bonds? Careful. Is hydrogen bonding a bond? No. So we've got polar covalent bonds and we have covalent bonds. Our product has covalent bonds. What does that mean for our intermolecular forces? Now, hydrogen bonding. We get our dipole-dipole and we get our LDF force for our starting material. And our product would have just our LDF. Okay? So we could go through and approximate what we might guess for our phases here. Do you think we have any solids within this? It's a bit tricky. Which one would you think would be the solid?
Whatever the alcohol.
First one, because we got hydrogen bonding, strong force, right?
Yeah.
How much hydrogen bonding do we have there? A lot or a little in comparison to the LDF?
A little.
A little. So while it may have a lower melting point or boiling point, there really isn't all that much. We're probably not looking at a solid. Okay? So then we're between liquids and gases. What are the odds we're going to make you work with it as a gas? Not very likely, so we're probably looking at liquids. Okay? So we've got 2 liquids to work with here. Okay? As far as the intermolecular forces go, the dominant force was our London dispersion force, which would mean these would likely mix. How do we separate 2 miscible liquids? Can't pipette them because they mix. Why heat?
They have different melting points. Or
We would expect their boiling points to be different. So what we can do is add heat. When we add heat, one of them will turn into the gas phase first, and that one then floats off into nothing, probably gets into our lungs, not a particularly good thing, so we come up with some fancier glassware, and instead we distill. So what we're going to separate these on is based on their boiling points. A boiling point is the point at which the vapor pressure of your liquid exceeds atmospheric pressure. Atmospheric pressure is what's holding your liquid as a liquid. Okay, your substance down. The heat that you've added into the system is enough to break the intermolecular forces. The vapor or your atmospheric pressure doesn't allow for the molecules to get far enough away from each other to completely destroy those intermolecular forces, okay, which is why we keep that liquid phase. Which of the two compounds is most likely to be a gas? Your product or your starting material? Product, because weaker intermolecular forces. We don't have that hydrogen bonding interaction. So the one most likely to be the liquid would be your cyclohexane or cyclohexanol starting material. As far as doing your distillation, you'll start with a reaction vial. Make sure you use the reaction vial and not the storage vial. What's the difference between these two? One's called reaction, one's called storage. That was kind of funny. If you take a look closer up at the glassware at the top, your storage vial has polished glass. If that's put together or if that bore was improperly done, it might sort of fit with your glassware, and you'd think it's correct until it started spraying chemicals, hot boiling chemicals out the sides of it. Okay? So in the interest of your TA, please don't use that one. Use the reaction vial, which has the powdered glass. That powdered glass will actually allow for a proper joint. Okay? Next thing is we need something to be able to collect our liquid or collect our product on. Our reaction is going to heat up. That's going to turn our product into a gas. That gas, will rise up inside our reaction or our Hickman distillation head, and it'll get up towards that top part of the glass. We're no longer heating. That's not against the hot plate, which means what happens to the temperature? It cools. What happens to a gas when you cool it down? Turns into a liquid. It condenses. That condensation builds up enough where it drips down into the Hickman distillation head. There's a little lip there. The liquid piles up until eventually what happens? Till it clears the lip and falls back down into the reaction. That's not a particularly good thing to happen. That's our product. So what do? Take it out. So you unscrew the side of your Hickman distillation head and you can pipette your product out the side. Okay? You will be pipetting out your product and water, just so you know. Just because we want to be excessive, we're also going to add a water condenser to this. So if for some reason your reaction gets really, really hot, air might continue to travel up. The water will help cool our condenser even faster or more efficiently, and we can try and trap our product inside even better. Okay? The very last thing we're going to attach is a drying tube. It is going to be there primarily just to collect vapors. Okay? Your product stinks, which means we want to try and keep it trapped as best we can. Okay? So the drying tube is still going to allow for air to pass through, but hopefully it'll trap all the chemicals so you won't have to smell your product quite as much. That's the hope. It's not going to work, but that's the hope. Okay? And just because I think this is fun, we could go ahead and put it all together. And we have our complete distillation apparatus. You'll notice there's little screw caps on there. Your TA in lab will show you what those screw caps are doing. They must be put together properly for this system to work correctly. Okay? One of the problems with this is that water is a side product in this, so we will get two things distilling across, water and your product. Would we expect those two substances to mix? Our product had no alcohol group. Okay, so no hydrogen bonding, just LDF forces. We would expect to see two layers. How can we separate or remove the water layer? We can just use a pipette. Okay? The next thing that we're going to do is add more water, but that water is going to come in with a lot of sodium chloride, so it'll be a saturated solution. Okay, why would we add more water after we just removed it? It's kind of a tricky question. The sodium chloride is already dissolved. Water will have some slight solubility in your product. So what we need to do is try and remove as much of that water as possible So we'll pipette out the bottom layer first, or your water layer, and then we add this saturated sodium chloride solution, much like salt water or ocean water. Okay? If you're trapped out on the ocean, what do they tell you about not getting thirsty?
Don't drink salt water.
Don't drink salt water. Why?
Makes you thirstier.
It makes you thirstier. It actually sucks the water out of your body to dilute the salt concentration. It's exactly what we're relying on with this wash. We're trying to pull the bulk of that dissolved water out as fast as we can, or as efficiently as we can.
When you're dehydrated, don't they give you saline?
Different situations, it comes down to what different causes are going on with that. That's a different medical thing. That's going to come down to electrolytes. The next thing is drying agent. Okay, so what we're going to add is solid sodium sulfate to this, a solid salt to remove the last of the water. Anybody know what that picture is on the right? Not maggots and sugar.
Yeah.
It's rice in salt. Why would we ever put rice in salt? The rice will soak up moisture instead of the salt. Well, why do we care about that? If we don't put it in there and we try and shake the salt can clump up around moisture, and we don't get salt coming out of our salt shaker. We're going to rely on that same principle with this. We're going to add the solid sodium sulfate into our reaction mixture once we've removed all of the visible water. The sodium sulfate, if there's any other water present, will wrap around the remnants of water, forming a salt clump. We now have transferred that invisible water into a solid. How do we separate the liquid from our solid? We can just filter. Okay? And that allows us to remove the last few traces of water from the reaction. One of the most common questions that students will get or students will ask is how much sodium sulfate to use. And everybody loves the answer. It's enough. It's different for every single student. Okay, so we can't tell you specifically how much to use. It depends how much water is still in your reaction. Okay, so you have to kind of get used to the differing amounts and what you're looking for. If there's water present, what does it do? Clumps around the water. What if there's no water present? It doesn't clump.
Can you use too much?
Yes and no. I'll discuss that in a second. So what you're looking for is a small excess of the drying agent to look the same in the liquid as it does inside the reagent bottle from which you pulled it out of. What is that? So frustrating. And now I've lost my train. What was your question?
Oh, if
Too much.
too much.
Yes and no. So, no, it's not going to lose your product. Yes, if you add so much solid to it, you end up not being able to see or get your liquid product out of it. Okay? In general, you're not adding that much. It's usually a couple like spatula tips full. Okay? Is it in here? I'll try and hunt it down in a second. Go ahead and pass out the group activity. The last thing you'll do is classify or identify your product. We're going to use IR and a chemical classification test. Which of those IR spectrum is your product, top or bottom? Why is the top your product? Because you've got the OH in the bottom one. Good job. You'll need that in a couple weeks when you take the exam, lab exam. So we've got that OH. Without that OH, we're probably looking at our product. The last classification test we're going to do is an addition reaction, which you learned in Chapter 5. Shay, we need another one over here at least, maybe. We're going to add bromine to your product. Bromine reacts with double bonds. Once the bromine reacts, it's no longer present. We no longer have that red color. You will also test it on your starting material. Why test the bromine on your starting material? so that you know it doesn't react. In theory, you don't know if your starting material has a double bond in it or not. Okay? So we'd want to test. If it went colorless with our starting material, what does that mean about the usefulness of the bromine test? It's pretty useless. We don't see a difference between them. Okay? That's just the general conclusions. And then we'll leave it on the resonance and mechanism slide. If you've got any questions, please raise your hand.